You know, every time you buy something online or even just stream a movie, there are tons of different systems in the background all talking to each other. But here's the crazy part. There's no single boss telling them what to do. So how does that chaos actually work? Well, it's not magic. It's this really cool process called leader election. And we're about to break down exactly how it brings order to that digital world.
Right, so this is the fundamental question. In a network where every computer is basically a peer, who's in charge? It's kind of like that awkward moment in a group project where nobody wants to step up. But in the world of computers, this isn't just awkward. It's a critical failure point that could bring the whole thing crashing down.
Because without a clear leader, you get pure chaos. Seriously, imagine going to an ATM and every single machine gives you a different account balance, or a cloud service where multiple computers are all trying to be the one source of truth for your data. That's the mess we're trying to avoid, and it's exactly why having one and only one designated leader is absolutely non-negotiable.
To solve this digital anarchy, computer scientists came up with a set of rules for how a group of computers can pick their own boss. And there's a formal name for this. It's called the leader election problem. Think of it like a high-tech version of drawing straws, just way more elegant.
Now, any good solution to this problem has to do two things perfectly. First, there can only be one leader. No co-CEOs, no confusion, just one. And second, everybody else in the network has to know and agree on who that leader is. If even one machine is out of the loop, the whole system is still at risk.
So, how on earth do you pick a winner from a group of machines that are otherwise identical? Well, you give each one a unique ID. It's basically a name tag, or like a bib number in a marathon. This simple number is the secret sauce that lets the network tell one computer from another and actually start the election process.
Okay, so let's dive into one of the first and maybe most intuitive ways to solve this. It was designed for a really simple network layout that's shaped like a ring. We can call it the Whispering Ring.
So the setup is about as simple as it gets. Imagine all the computers are sitting in a circle, and each one can only pass a message to the neighbor on its right. That's it. It's just like a game of telephone or passing a note around a classroom. In computer science, we call this a unidirectional ring.
And this is where those unique IDs become the star of the show. It's an algorithm called Chang-Roberts, and here's how it works. Any computer can decide to start an election by whispering its own ID to its neighbor. When a computer gets a message, it looks at the ID inside and compares it to its own. If the incoming ID is smaller, it's a weaker candidate, so that message just gets thrown out. But if the ID is larger, it's a stronger candidate, and it gets passed along to the next computer in the ring. So who wins? The computer whose ID is the highest. It's the only one whose message will make it all the way around the circle and back to itself.
It's simple, it's elegant, and it absolutely works. It always guarantees you get one unique leader. But, and you knew there was a but, there's a huge, costly catch hidden inside all that simplicity.
The problem isn't about whether the algorithm works. It totally does. The problem is what it costs. Because in certain situations, this super simple approach can create an absolutely catastrophic traffic jam of messages on the network.
Okay, let's break down that cost. In the best case scenario, let's say only the computer with the highest ID decides to start the election. The number of messages is pretty low, just about O of n, or proportional to the number of computers. No big deal. But what happens in the worst case scenario? What if every single computer decides to run for leader at the exact same time? Well, the number of messages doesn't just go up a little bit, it explodes into what we call O of n squared.
Now, n squared might just sound like a math term, but let's put it in perspective. For a small network of, say, 10 computers, that's maybe 100 messages. Manageable. But for a network of just 1,000 computers, that could mean up to 1 million messages flooding the network for one single election. That's not a traffic jam anymore. That's a total system meltdown.
And really, that's the bottom line. A potential million message pileup for a simple election is just flat out unacceptable for the kinds of large systems we all rely on every day. So for all its elegance, the simple whispering ring is just way too chatty when everyone tries to talk at once.
So clearly, we need a better way. And this brings us to a much, much cleverer upgrade. It's a smarter method that completely solves this traffic problem by basically changing the rules of the game. The first big change is the network itself. Instead of only being able to whisper to the neighbor on your right, what if you could talk to the neighbors on both your left and your right? This simple upgrade, creating what's called a bidirectional ring, is what unlocks a far more efficient strategy. This new strategy is called the Franklin algorithm, and the best way to think about it is like a knockout tournament.
Instead of every candidate's ID having to race around the entire ring, they now compete in these quick, local rounds that rapidly eliminate the competition.
Here's how it works. Since computers can talk both ways, they can have these little local showdowns. In round 1, you only compete against your immediate neighbors. If you have the highest ID in that tiny group, you survive and move on. In round 2, the survivors then compete with their neighbors who are 2 steps away, then 4 steps away, then 8. The search area literally doubles each round, which means weaker candidates get knocked out incredibly fast, long before their messages have a chance to clog up the network.
And the power of this is just how fast it narrows the field. You could just see it. The number of active candidates plummets. It gets cut by at least half with every single round. You go from having 1,000 potential leaders down to just 1 in a tiny fraction of the time and with way fewer messages.
So now we've got 2 very different approaches to solve the exact same problem. Which brings us to the big question. How do you choose which one to use? Well, it all comes down to a classic engineering trade-off: simplicity versus efficiency.
Let's put them head to head. Now here's what's really interesting. They both actually take about the same amount of time to finish an election. The real game-changing difference is the number of messages sent. While that first algorithm risks an O of n squared meltdown, Franklin's tournament model is way more efficient at O of n log n. That means the number of messages grows much more slowly as the network gets bigger.
In fact, the Franklin algorithm is pretty much as efficient as you can possibly get for this kind of problem. It's a solution that scales beautifully. You can keep adding more and more computers to the network without having to worry about the communication costs just spiraling out of control.
So, at the end of the day, this is the choice an engineer has to make. The first algorithm is simpler to build, since it only needs that one-way communication. But the second one, while it needs a more complex two-way network, gives you vastly superior performance by preventing those awful message traffic jams. There's no single best answer, just the right tool for the job.
And this is why this all matters so much. These aren't just abstract ideas. These algorithms are the secret sauce that makes our modern internet so robust. They create self-healing systems. When a server that's acting as a leader crashes, a new election just kicks off automatically, a new boss is chosen, and whatever service you were using just keeps on working without a single blip. It all just happens right in the background.
Which leaves us with a final thought that goes way beyond just networks. In any complex system you can think of, is a simple but potentially fragile solution ever a better choice than one that's more efficient but also more complex to build and maintain? It's a fundamental question that engineers, and frankly, leaders of all kinds, have to wrestle with every single day.